In the Chapter 12a PowerPoint, we talked about some of the basics about tornadoes, and now we're going to move on to a topic called tornado outbreaks, and that's defined as when a large number of tornadoes, typically 6 or more, form over a particular region, and there are some infamous tornado outbreaks in United States history. March 18th, 1925 was the date of the devastating tri-state tornado. April 3rd to 4th, 1974 was an outbreak that caused 315 deaths and over 6,000 people were injured there. The combined paths of all the tornadoes on the ground was almost 2,600 miles. May 3rd, 1999, suburban Oklahoma City, that spilled also into southern Kansas. One particular tornado was a mile wide, and indirect measurements of winds with Doppler radar indicated the winds around that tornado may have reached as high as 318 miles an hour. Now, after this textbook was published, in April of 2011 and in May of 2011, there were two particularly destructive and deadly tornado outbreaks. And I have the link. If you play this PowerPoint properly and actually click onto this link, or maybe just cut and paste this link and put it into a browser, you'll be able to examine the severe weather report by the Storm Prediction Center, the SPC, for 2011, and focus in on April and May, and you will be just astounded at the statistics for tornadoes during those two outbreaks, which were particularly deadly. Prior to the April and May 2011 outbreaks, these are the lists of the 10 deadliest tornado outbreaks in U.S. history, up until the point, of course, that the ink was dry on your textbook. The next one shows you the 10 largest tornado outbreaks with respect to the largest number of tornadoes that were counted in an outbreak. I have two maps to show you now. This is the surface weather map for April 3rd, 1974, showing very strong surface convergence, or a low-pressure center over central Kansas. Very warm, humid air moving up from the Gulf of Mexico, and the warm wedge, if you will, in the open wave section of the mid-latitude cyclone. And, of course, much colder, drier air coming down from the backside. The corresponding map I'm about to dissolve to now shows the paths of tornadoes that reach the ground in the April 3rd, April 4th, 1974 super tornado outbreak. And you can see that the paths of those tornadoes on the ground stretch all the way from east central Mississippi all the way to Windsor, Ontario, Canada, just across the river there from Detroit, Michigan. So it's quite astounding when you consider that the length of the path of all those tornadoes combined was almost 2,600 miles long. Here are some very poignant pictures from the destructive tornado outbreak in central Oklahoma through southern Kansas of May 3rd, 1999. On the left, the tornado, the EF5 tornado, was approaching a suburb of Oklahoma City called Newcastle. On the right, a picture taken several days after the May 3rd, 1999 tornado in suburban Oklahoma City. I mean, really total devastation on the surface. It looks like a war zone. It really, really does. The strongest tornadoes we know of are called supercell tornadoes, and they form from supercell thunderstorms. And in Chapter 11, we discussed the climatology for the formation of supercell thunderstorms when you have a single rotating tilted updraft, counterclockwise updraft, in the entire height of the thunderstorm called the mesocyclone. It can last for hours. You have that strong directional shear and wind shear, or directional shear and speed shear going up from the surface, where the winds veer in direction and rapidly increase in speed. The air near the surface in this situation rotates about a invisible horizontal axis, much like you would hold a pencil up and rotate it, a vortex tube. This is caused by a southerly low-level jet stream with very warm, moist air from the Gulf of Mexico, just above the southerly surface winds, a few thousand feet up. And then you have they have stronger winds aloft. This is a schematic diagram of a supercell thunderstorm with the potential for forming a tornado. The colors on the surface of that map, the green indicate light precipitation, the yellow indicates moderate precipitation, the red indicates heavy precipitation, and you can see that that's almost in the shape of a fish hook. So keep that in mind as we continue to discuss the parameters of tornado development in the rest of this chapter. There is an illustration, figure 12.19a, showing the strong horizontal axis that develops as surface winds come in from the south with warm, moist air, and winds aloft come in from the north. That's cold, dry air. And then eventually you get updrafts as the cumulus cloud forms, which takes that horizontal vortex tube and lifts it into the vertical, providing the mechanism for the formation of that mesocyclone, which goes the entire height of the thundercloud. This updraft, as I mentioned in Chapter 11, is so strong that precipitation can't fall through it. The southwesterly winds aloft carry the precipitation northeast, especially if the storm is moving from southwest to northeast, which they typically do. It wraps around the mesocyclone in a counterclockwise fashion. The area in the mesocyclone where radar can't detect precipitation is called the BWER, or bounded weak echo region. And then, of course, you get that classic fishhook shape or hook echo that you see on the radar with the precipitation patterns. This is the reflectivity radar image, meaning showing where precipitation is most intense, of the supercell thunderstorm that produced the EF5 tornado in suburban Oklahoma City on May 3rd, 1999. Now, if you go back to figure 12.18, and take a look at this figure and see how the precipitation pattern is very similar to this cartoon, and look at it in reality, the reflectivity image of that particular supercell thunderstorm that produced the tornado over Oklahoma City, which is basically right here where this number 26 happens to be. In the supercell tornado structure, at the back of it, you've got what's called the rear flank downdraft, and that's said to be instrumental in producing tornadoes in classic supercells. That can move forward and interact with the forward flank downdraft, where the initial gust front comes down, to initiate the formation of a tornado. This decreases the supply of warm air to the mesocyclone, which causes the mesocyclone to essentially stretch out, or thin out, or attenuate, and get taller and thinner. Much like those crazy little toys you had when you were a kid, you put your finger in and you couldn't pull your fingers out, that kind of a thing. It causes the tornado to attenuate or become thinner, stretch upward and spin faster, forming a tornado vortex. Here is that same graphic, but I wanted you to see the stepped art. If you're actually playing this PowerPoint in the play mode and not looking at the slides individually, as I'm doing when I'm recording this, you can see the stepped art, and you'll see all the features of a supercell tornadic thunderstorm gradually layer in, so you can see how this is put together schematically. Now, you can get tornadoes from non-supercell tornadoes. Tornadoes that do not occur with a pre-existing wall cloud or a mesocyclone in the supercell. They can occur with multi-cell thunderstorms and occasionally with air mass thunderstorms. Some extend from the base of a cumulonimbus cloud, and others begin on the ground and build upward. We've seen both, or scientists have seen both. If those non-supercell tornadoes form in an association with the gust front of a thunderstorm, where the cool downdraft forces warm, humid air upward, they are often called gustnadoes. They're relatively weak and they don't last very long, and they rarely cause extensive damage. You can also get tornadoes that form with rapidly developing towering cumulus clouds with no mesocyclone in the thundercloud. They're sometimes called landspouts, and sometimes in California when we have a few tornadoes, they're often referred to as landspouts. Another way of illustrating how a landspout can form, let's say you've got a towering cumulus cloud forming along that dotted line there, which shows winds that are coming in from opposite directions, a convergence zone, if you will. And if that cloud happens to go right over a place where there's some spin in the lower atmosphere, where those winds from different directions are converging, then you can get a landspout that can form with a non-supercell tornado. Some of the small tornadoes and/or funnel clouds we have here on the West Coast are often formed in association with thunderstorms that form because of cold air aloft after a cold front has passed through the area, and the upper level storm or trough is still hanging over the region. These are often called cold air funnels. This is a great photograph right out of your textbook, figure 12.25, of a cold air funnel taken some time ago near Lodi, California, up there in San Joaquin County. And then we have something called a waterspout, which is a rotating column of air that's connected to a cumulonimbus cloud or a cumuliform cloud, which occurs over a large body of water. They're very frequent over the Gulf of Mexico because of the very warm, moist conditions there and along the Florida coast, either side of the Florida Peninsula. This photo, which is figure 12.28 from your book, actually shows a rare waterspout over Lake Tahoe, California. A little bit closer to home. That's really a spectacular photograph. Now let's talk a little bit about how the National Weather Service Doppler radar network helps us see the structure of severe storms. Because the radar sees precipitation particles and they're carried by the wind, we can examine the structure of these storms and how their winds behave. Now, so far I've shown you reflectivity images from National Weather Service Radar Network. It's called the WSR-88D. 88 stands for 1988, which was the year it was developed. D means Doppler. WSR is short for Weather Surveillance Radar. In any case, I've shown you so far reflectivity images from this radar network, which show the intensity of precipitation on the ground that comes out of the cloud. However, there are other useful images from this radar which are called storm relative velocity. That can show the close packing of horizontal winds which are moving toward the radar and horizontal winds that are moving away from the radar, and that indicates strong cyclonic rotation and the possible presence of a tornado. So pay attention to this next graphic, 12.26. Do you see about in the middle of that graphic, to the left of that clear black dot, which is, by the way, the location of the Oklahoma City radar, how the orange pixels and the yellow pixels are very, very close to the green pixels and the blue pixels? That indicates where you've got a very strong packing of winds blowing toward the radar and away from the radar. This indicates a strong counterclockwise rotation or cyclonic rotation, and that is where that EF5 tornado was at the time this storm relative velocity image was captured on the Oklahoma City radar on May 3rd, 1999, when that EF5 very destructive tornado hit suburban Oklahoma City. It certainly is one for the record books. Since these radars that the National Weather Service has, and even though there are 160 of them across the nation, about 119 of them are associated with Weather Service offices, and the other 41 of them or so are associated with Department of Defense sites. There are gaps of data in between, especially when these radars are in sparsely populated areas, because they don't tend to put a lot of them in a really fine mesh in sparsely populated areas, because they're supposed to serve densely populated areas. So what you have then are researchers from, graduate students, say from the University of Oklahoma or other places, that go out with these Doppler radars on wheels, or DOWs. Sometimes they're on the back of a semi-truck, sometimes they're portable and they take them out into a field. And of course, you don't want to get too close to the tornado. As they say, don't try this at home. But this picture shows from your textbook graduate students out on assignment, trying to get as close to the tornado as they can, obviously staying out of harm's way, and to be able to collect additional data to fill in the gaps where the network of National Weather Service Doppler radars simply can't reach. There are computer programs in these radars called algorithms, which are embedded in the Doppler radars. They help to detect and measure severe weather phenomena so that scientists can hopefully gain a better understanding of these very awesome and destructive forces of nature. This concludes PowerPoint Chapter 12b.